Okay, in this activity, we're going to practice a couple different problems that utilize various combinations of the complement and the multiplication rules. Okay, in this first one, we have a student finds that his car's alternator fails 10% of the time. The way we would note that 10% of the time, our probability would be 0.1. Now notice I made a note up here that if it fails 10% of the time, 90% of the time it's going to start. I'm just hoping that you will eventually be aware, conscious of probability and its complement as you're working through problems. Okay, what is the probability that his car will not start the next 5 times? Well, each time that he attempts to start his car, that's a separate event. So we're looking at 5 different events, each of them having a probability of 0.1. So that would be 0.1 to the 5th power. What is the probability that his car will start the next 5 times? That's starting the next 5 times. That's what we're thinking about. That complement would be 90% that it will start. Each time that he attempts to start it is going to be a separate event, so we'd have 0.9 to the 5th power. So we'd end up with 591 thousandths probability. Okay, the next one, we're looking at a knee surgery. Probability that a particular knee surgery is successful is 85%. I'm noting that the complement of that is 15%. Just kind of be on the ball here. Find the probability that 3 knee surgeries are successful. Each surgery is a separate event, each of them having the probability of 0.85. So we'd say 0.85 to the 3rd power. Find the probability that none of the 3 surgeries is successful. That's that complement, not successful. Each surgery is a separate event, so that'd be 0.15 to the 3rd power. Okay, this is a little tricky, but we're looking at least one means one or more. The complement to the event at least one successful is the event none are successful. We'd be using the complement rule that the probability of at least one is successful is equal to 1 minus the probability of none are successful. Basically, that just sounds like an awful lot of syllables there. But let's go back to this problem here with our knee surgery. We know what the probability is when all 3 are successful, and we know what the probability when none of the 3 are successful. But we didn't calculate when 2 are successful or 1 are successful. We've got kind of a gap in there. And now we're going to be looking at finding the probability that at least one of the 3 surgeries is successful. At least one would include 1 being successful, 2 being successful, or 3 being successful. And that would be the whole sample space other than, it's lacking, the probability of none being successful. So we can see that kind of makes sense that these two concepts, at least one and none, are going to be complements of each other. So I know that the probability of none of the 3 surgeries being successful is 0.003. So the complement to that would be 0.997 probability that at least one is successful, which would include 1 being successful, 2 being successful, or 3 being successful. Just doesn't include this one here. Okay, the next part here, we're going to take a look at redundancy. That's a concept that comes into play in different electrical systems or any kind of design systems. Engineers design redundant components so that the whole system will not fail because of the failure of a single component. In airplanes, there will be 2 electrical systems because if one fails, we don't want the plane going down, we've got a backup. There's a story about the Challenger, which exploded, where they didn't have a backup system, or they didn't practice this principle of redundancy in some of their design, and therefore had a terrible tragedy. So it becomes very important. Okay, we're going to look at something that's not quite as drastic, but your alarm clock has a 90% chance of working on any given morning. What is the probability that your alarm clock will not work on the morning of the exam? So just straight up, you're dealing with complements there. 0.9 is the complement to 0.1. So we've got a 10% chance your alarm is not going to go off on the morning of the exam. Okay, but if you have 2 alarms, what is the probability that they will both fail on the morning of the exam? So we have 10% chance of either alarm failing. Each alarm is its own event, so we're going to multiply those 2 probabilities to have a 1/100th chance or probability that both clocks will fail. Well, just thinking about that, if you have a 100th chance of both clocks failing, that means that you've got a 0.99, or the complement of that is 0.99, or 99% chance that one or the other or both of the clocks will work. Okay, so if the probability of being awakened with 1 o'clock is 0.9, what is the probability of being awakened if you set 2 alarms? And that's what I just discussed there. But this is writing out all the mathematical equation that you would use. Probability of at least 1 clock works is equal to 1 minus the probability that both clocks fail. I just don't think you're going to pull out that problem. I think you'll reason it as I discussed it up here. So 1 minus the complement of both clocks failing is 0.99. Okay, acceptance sampling is a practice where manufacturers randomly select units from a production line. They test for defects and accept the entire run if the sample is okay. Companies do this when they're receiving product from their suppliers. They also, want to check to see that the batch that they have coming in, or the shipment that they have coming in, is good, and so they can't check every single one of the items, so they select 2 or 3, or they have some policy for how they do that. So that's the same kind of concept here. A company knows that generally 1 in 50 items will be defective. So what is the probability that if 3 units are selected, the batch will be accepted? In other words, they will accept the batch if they select 3 and they're all good. So we want to go back to first finding out the probability of a defective item. And that's what we're doing right here, is that the probability of a defective item is 1 in 50. We got this 1 in 50 here, so it would be 0.02. The complement of that is, if selecting an item and it has a 2% chance of being defective, the complement of that is that it's got a 98% chance of not being defective. So we want to know what are the chances of getting 3 non-defective items in a row, each of them being their own event. So that's how you get that 0.98 to the 3rd power. Okay, the probability of randomly selected car crashing during a year is 48,000th probability. If a family has 4 cars, find the probability at least one will crash during the year. So insurance companies would be looking at this type of reasoning for their multi-car policies. So the probability of a single car not crashing is going to be the complement of it crashing. So we're going to take 1 minus the 0.048 to give us 0.952. That's the probability of any car not crashing in that year. The probability of 4 cars not crashing is going to be the probability of a single car not crashing 4 times, because each car is its own event, which is going to give us the outcome of 0.821, or 821 thousandths probability that no car will crash. So our last question is, probability of at least 1 car crashing is going to be the complement of no car crashing. So 1 minus the 0.821 is going to give us our 179 thousandths probability for at least 1 car crashing.